Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Chris Smith. Any new exciting stories in the world of science?
Well, there's always exciting stories in the world of science, but this one really caught my eye, which is a wonderful story about malaria. And malaria we tend to dismiss as a problem which doesn't happen here, but of course remember that it wasn't that long ago that in fact fen ague was a major problem, and that was malaria. We used to have malaria rife in the fens until it got wiped out by draining the fens, and that meant the mosquitoes no longer had anywhere to live. But the key thing about malaria is it affects about 200 million people around the world every year, and a lot of them are young people, a lot of them are children, and it unfortunately leads to up to 2 million deaths, so it is a big problem. And up until now, we haven't really had a big drive to make any more malarial drugs because there haven't been any wars in the tropics lately, and because it doesn't tend to affect the first world, there's not much profit in making anti-malarial drugs, so pharmaceutical companies haven't been very interested in it. And as a result, the medicine chest is looking really rather bare when it comes to good quality anti-malarials for which there isn't resistance in the malarial parasite. So researchers really need to go looking for new targets to aim drugs at. And that's exactly what's happened this week. There's a paper in the journal Nature, and it's from a group of researchers in Australia. This is Tanya de Koning Ward, and she's at the Walter and Eliza Hall Research Institute, which is in Melbourne. And what they've managed to do is to solve a big problem in malaria, which is that this parasite lives inside our red blood cells. And it's very interesting because if you look at it under the microscope, you can see these little things, these little circles that stain purple inside red blood cells if you look at the blood of someone with malaria. And the thing is, the parasite is inside a bag, inside that cell, a sort of vacuole as it's called. And so there's a bit of a problem for the parasite. How does it get things that it makes, that it wants to use to hijack and control that red blood cell to make it the ideal environment for making more malaria? How does it get the things it makes out of the parasite and into the rest of the cell? Because malaria does some very interesting things to our cells. One of the things it does, for instance, is to decorate the surface of the cell with very sticky molecules that are the molecular equivalent of Velcro. And the effect this has is that when the malaria-infected red blood cell drifts along a blood vessel, then because it's sticky, it tends to jam in the vessel. And that means that then it keeps the malaria out of the clutches of the immune system, because if that red blood cell was to wander through another organ like the spleen, where the immune system can get it, then the parasite might be destroyed, or at least its home would be lost. So by jamming the blood cells in different blood vessels, it's a way of protecting the parasite. How does it get those things out of the parasite and onto the surface of the red blood cell? Well, what these researchers in Australia have found is that the parasite puts together a sort of clutch or a handful of different proteins that it makes, and these assemble on the wall of this vacuole around the parasite in the cell, and they form a structure called a translocon. This is like a revolving door, which selectively picks up some of the things that malaria makes, feeds them through this little pore, and then they assemble on the other side and go off and do their job. And the amazing thing is that each of the things that are supposed to go through this pore, each of the proteins and other chemicals that malaria is making, they are tagged with a special label, which is like the key to this door. And so when the door sees this label, it opens like open sesame just for those particular those proteins, and they go through. And what's exciting about this is that apart from answering a very important question, how do these things that malaria makes get out into the cell it's infecting? Also, when they compared the structure of this channel to similar things that other parasites and other animals and other organisms make, there is nothing like it anywhere else in the literature. And why that's important is that means that if you made a drug that could block it, if you could do that selectively, you're going to have very few side effects because the drug isn't going to interfere with anything that's normally found in a healthy person. So it might mean that this is a new way to make a whole new class of anti-malarial drugs. So it's a big problem, and this could be one way to solve it. So it's a wonderful story, and you can find it in this week's edition of the journal Nature.
Wonderful, Dr. Chris. First of all, we have an email from Ben who says, love listening to the show every night and science the best bit. If you ask Dr. Chris my question, could it be earlier in the show as I usually go to bed and I don't want to fall asleep because I'm only 9? Ben, we love you. So, Chris, Ben asks, he would like to know, as the world is spinning at 1,000 miles per hour, why is it that when you jump up and down, you don't end up somewhere else?
Yeah, hi, Ben. The answer is that he's quite right. The equator of the Earth is spinning at about 1,000 miles an hour because the Earth being a ball in space, if you stood at the North Pole, of course, that's not turning very much because you're not going very far. But at the equator, it's about 24,000 miles all the way around the Earth, and therefore, since the Earth does one complete turn every 24 hours, that's a day, the equator is turning at about 1,000 miles an hour. So what he's asking is, if he jumps up in the air, why doesn't the Earth turn a bit under him and then he comes down a little bit behind where he jumped? Well, the answer is that when you're attached to the Earth's surface because gravity is pulling you down and hugging you onto the surface of the Earth, of course, you're also moving at 1,000 miles an hour. So if you jump up in the air, you don't just go upwards, you also go along a bit. But because the Earth is moving with you, you don't know that you've moved along a bit. So when you come down exactly where you took off. And it's a bit like if you're standing on a train and the train is moving along at 100 miles an hour and you jump up in the air, you come down in the same place in the carriage because relative to the carriage you're not moving, but relative to the ground both you and the carriage are moving, and therefore you have velocity with the train. You don't get left behind. And it's a good thing, really, isn't it?
I would think so, yes, absolutely. All right, Ben, I hope that answers your question. It does mine. I understand it now. Now, Chris, Anne has sent you a love and a hug as well, but she says, does really long hair in a man or woman take a certain amount of your strength? I used to hear it and I wanted to know if it was a myth or if there is any truth in it. Chris?
Well, I haven't got really long hair, and I'm not really very strong either, so I guess I buck the trend. But Samson, of course, was the biblical character who, when he cut his hair off, he lost all his strength. So he kind of is the opposite. But the answer to Anne's question is the hair is dead. So once the hair is grown, then it's not in any way extracting any energy or taking from you any kind of nourishing requirements, if you like. But to grow the hair in the first place does take good nutrition because hair's a protein. It's a protein made of keratin. It's the same stuff actually that makes your fingernails. It's in a slightly different form when it's in your hair. And this is basically a plaited form of protein chains. You plait the protein chains around themselves and they form this strand which is hair. It comes out of hair follicles. Because it's made of protein, it therefore needs a good diet rich in protein to make the hair in the first place. So someone who is malnourished and people who have eating disorders who don't get enough calories and they don't have enough protein in their diet, they will have poor quality hair. So you can tell people who are malnourished because their hair may fall out, it may grow very slowly, or it may be very thin and weak. And people who are well nourished, the reverse is true. On the other hand, you don't find that once your hair has been grown, it in any way extracts further energy or requires further maintenance from you, over and above just washing it from time to time. So I don't think there's any evidence linking hair and strength in that respect.
Now, it's Dom this time, who says, why is it when you take in helium, it makes your voice higher?
Yeah, this is an effect due to the speed of sound. Helium is a much less dense gas than air. It weighs a fraction of the amount that the air does that we normally have in our vocal tract. And as a result, sound travels much faster in helium than it does in air. So when you take a breath of helium in, what's happening is you're mixing the helium that you breathe in with the air that's already in your lungs. And so when you start to breathe out, you end up breathing out a mixture which is much higher proportion of helium than normal air. So you've got a mixture of air now in which sound will travel a lot faster, and therefore your vocal folds will have harmonics, which are, when you make something vibrate, you have your initial harmonic, and then you have second, third, fourth, and so on harmonics, which are multiples, or they are divisions or multiples of the wavelength of the first harmonic. And because the sound is travelling faster, you will exaggerate some of those other harmonics in your voice more than others. And specifically, you will exaggerate the higher frequencies with the shorter wavelengths more than you would do normally. And this means that the sound that comes out is therefore the same sound you would normally make, except that the higher registers are emphasised, and as a result, the timbre of your voice actually goes up. The actual voice doesn't change. It's not doing anything anatomically to your vocal cords. It's just affecting the sounds that tend to get amplified in your mouth and come out, because sound travels much faster in helium than it does in room air. And so as you slowly breathe out more of the helium and you get down to normal air again coming out, then the effect goes away.
Excellent. Thank you very much, Dr. Chris. Now then, Brian from Roxwell says, an old naval joke pulled on the midshipmen and cadets. Which part of a sailing ship travels the furthest? The mastheads, as they are further away from the sea, or the earth?
Well, it depends. When you're going sailing, of course, there's two different speeds that you talk about, because you can have a speed over the water and then you can have a speed over the ground. And a good way for me to explain that is, if the tide is going in the same direction that I am in my boat, then I can actually be sailing over the water at, say, 10 knots. But if the tide is running at 5 knots, then my difference in speed between the boat and the water is 10 knots. But the water's going at 5 knots. So if you add the two together, you actually got 15 knots of movement of the boat over the ground. So if relative to the seabed, my boat's actually apparently going a lot faster. If the tide's coming the opposite way to the way my boat's sailing, say I'm sailing along at 10 knots and the tide is running at 5 knots in the other direction, although my speed over the water is still quite high, relative to the seabed, I've actually got to subtract one from the other, so I'm only doing 5 knots. So I'm not sure if that actually answers the question, but in fact, it's an important consideration.
Absolutely. Now then, Stacey says, when someone has hiccups, if they eat a cola bottle sweet, do the hiccups go? We have tried it on 6 people now, and it's worked every time. Any explanation, Chris?
Were those cola bottle sweets the fizzy variety? My favourite.
Yes, mine too.
Because I wonder if the person who got the cola bottle was so shocked at the fizziness that it took their mind off the hiccups. Hiccups are a diaphragmatic spasm. What's going on is that the part of your brain which controls your respiratory rate, it's in the brain stem, which is the structure that connects your spinal cord to your forebrain, the main part of your brain. And in there is a structure called the respiratory centre. And this is a cluster of nerve cells that are connected together, which are monitoring various things, including how much oxygen and carbon dioxide there is in the blood and in the brain. They're also measuring how filled with air your lungs are, and they integrate all of those things together, and they work out how much you need to breathe and when to make you breathe in, when to make you breathe out. Somehow, and for some reason, when we get particularly nervous, excited, tired, there are various stimuli, we don't really know what they are. This can make this circuit start to introduce these unusual hiccuping rhythms. And what happens is that the diaphragm, instead of contracting steadily in one long contraction, and this means that at the base of your thorax, you have this big muscle, the diaphragm, which contracts and goes downwards. This normally increases the volume of your thorax. So in other words, the pressure in there drops. And this means that the atmosphere then pushes air into your lungs to make them fill. For some reason, when we get the hiccups, then instead of that happening in that nice, coordinated, long fashion, instead the diaphragm suddenly jerks and it contracts a bit and then stops, contracts a bit and then stops. And so what you get are these rapid indrawings of breath. And that's what a hiccup is, because even if you're in the middle of saying something, in other words, air trying to come out, all of a sudden your breathing process is reversed momentarily. And so the air that was coming out starts to go back in again quite quickly. And that's when you get that hiccuping. We don't know what causes it, apart from what it's associated with. We do know that there may be a genetic component, and it can occur pathologically. There are some diseases, and sometimes people who have strokes or injury to the brain can develop pathological hiccups. And there was one man in America who had hiccups for 76 years, and I don't think anybody managed to cure him. So basically, something which can break that cycle or remove the set of affairs or state of affairs that made it happen in the first place usually manages to make it go away. And so all these remedies, like drinking from the wrong side of a glass or drinking some water or getting a surprise, they're all things which take your mind off the hiccups and make you focus your attention wholeheartedly on something for a period of time. And this, presumably in some way that we don't understand, breaks that cycle and enables you to focus on something else. The interesting thing is that babies have hiccups and other animals have hiccups. So it can't just be, it's not just a human phenomenon.
Yeah.
And some people suggest that babies hiccuping in utero is all about helping to move fluid in and out of the lungs. So it's almost like a respiratory exercise for them. And it may be a way of moving things in and out of the lungs to help to expand and promote development of the lungs. But I don't think anyone knows for sure.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. All right, well, we've got a caller now. We've got Chris on the line. Hello, Chris.
Hello there.
Hello there. You're through to Dr. Chris.
Yeah, hello there. I've actually spoken to you once before about my granddaughter, who they thought had a cyst on her lungs. It turned out to be a set of cells, apparently, from when she was born, that didn't have sort of anywhere else to go. And I'm wondering if those cells were part of the fetus as such, why they weren't given a specific job to do, you know? They've just sort of attached themselves to her lungs and grown over the years, you know?
Do you know, I'm really pleased to hear that she's okay. The simple answer is, Chris, that when the body of any animal develops, there's massive oversupply. You produce lots and lots more cells than you actually need. A really good example of this is look at your hands, and what you see is that you have webbing between the bases of your fingers, but certainly most of the distance along your fingers, the fingers are completely separated from each other. But if you look at a baby that's in the early stages of development, what you see is not individual fingers, although you can see where they're going to be. What you see is a flat plate of cells with no web spaces between them.
Yeah.
And what happens as the fetus develops is that the body knows where to keep cells alive and where to kill them. And cells commit suicide. And this is a process called apoptosis. That's a Greek expression which means the falling of leaves. And it's literally like that. It's like a tree getting rid of the leaves it doesn't want. Well, bodies get rid of cells they don't want during development. So we basically produce something by, it's a bit like a sculptor when they start with a big chunk of stone and they chip away the bits of stone they don't want to reveal the statue that they want to make. The body's very similar in the way that it puts itself together, and cells when they're made or born, they're given a sort of genetic address. They have a genetic program running in them that dictates where they're going to go, what they're going to do, and ultimately for some of them when they have to kill themselves, and those cells get chucked out. Sometimes, and for some reason, that genetic programming may not be absolutely right in one clutch of cells, and they may follow their own genetic program, or it's a bit like your computer crashing. Before it executes the final stage of a program, they don't get their final address, and they don't get told to turn off and kill themselves. And I suspect that that's probably what was going on here. You had this bunch of cells that didn't quite migrate to where they were supposed to go, and they didn't get the death signal to turn themselves off, and so they just sat there. And in fact, probably this sort of thing is actually very common, and you don't, for the most part, know about it, because for the most part it does no harm whatsoever, and probably most of us are drifting around with some kind of embryological abnormality inside us, if you like, but we don't know about it because it doesn't cause us any kind of ill health.
All right. Okay, thanks very much for that.
It's a pleasure.
Absolutely. Bye. Thank you, Chris. Thank you.
Bye.
Mike in Colchester would like to know, how do the sewage farms, how do they move all the waste around aeroplanes safely, and where's it all going and how?
The thing with aeroplanes is, of course, that if you had all of the stuff in one place, there's a danger that it could affect the trimming of the aircraft. So I think that when aircraft are designed, it's done with certain amounts of weight in mind. And so what they'll do is they will have the tanks fairly centrally disposed or balanced on each side of the aeroplane, so that there ought to be no problem with it, meaning that you get too much on one side or the other. I think that they're pretty well organised like that. And also, for instance, the amount of water that goes into the waste, probably large amounts of it comes out of the flush tank anyway, so you're just pushing water out of one tank and into another, and if they're disposed sort of next door to each other, then there shouldn't be too much of a problem.
Sure. We have Les on the telephone. Hello, Les.
Hello.
Hello there, you're through to Dr. Chris. What's your question?
Hello, Chris.
Hey, Les.
After burning the chili the other week, I thought, what would happen if you actually cooked these things in a vacuum, which would lower the boiling temperature? Would it still actually stick to the bottom of the saucepan, or quite what would happen?
The reason why things stick is not actually to do with the air pressure so much. I mean, most of the reason why this happens is because the heat from the gas flame forges or new chemical reactions to occur between chemicals which are in the meat and the sugars specifically in the meat and the surface of the pan and anything that's stuck onto the surface of the pan. And what effectively happens is that the sugar molecules which are in meat, because all meats are proteins and they're proteins which have sugar molecules attached to them, they're called glycoproteins. When you heat sugar up, you get caramel, of course, and when you burn meat onto a pan, what it's doing is caramelizing, carbonizing effectively the sugar. So when you caramelize sugar, it makes a chemical reaction happen where the sugar molecules change from one configuration to another, and they make new linkages to other molecules around them, and you get these big sort of polymers formed. And that's what's basically happening on your saucepan, and they're very sticky, so they adhere to the surface of the pan or the saucepan. And it wouldn't actually matter if you did it in a vacuum, because even though there would be no pressure, assuming you could still get your gas light underneath the pan, there would still be lots of heat, and so these sugar molecules would still undergo these caramelization transformations, and they would stick. But they're not bad news, these caramelizations, because there was a French chemist who was around in Paris about 100 years ago, Maillard, and he actually is the guy who's credited with the discovery of the Maillard reaction, and this is what makes our food taste so delicious. At 148.9 degrees and above, you get the Maillard reaction, which is where sugar molecules join up with nitrogen-containing protein molecules, and you get this new kind of linkage formed between the two, and this produces all these lovely aromatic compounds which taste so good, and that's why fried food tastes much better than boiled food, because when you boil something, the maximum temperature it can get to is 100 degrees C, whereas when you fry something, of course, there isn't that constraint because you're not reliant on the boiling of water, so the temperature can go higher, it can exceed 148 degrees, 149 degrees, you get the Maillard reaction, and you put those lovely caramelised things onto your food, and it tastes fantastic.
Enjoy. Thank you very much, Les.
Yeah, okay, thank you. Oh.
Right, our next question here, let me just get across here. Hi Sue, hi Chris. Could you please tell me how beta blockers slow your pulse? From Alan in Chelmsford.
Sure. Well, beta blockers block a class of chemical receptor or docking station called beta adrenoceptors, and the clue's in the name. Adrenaline and its chemical relative noradrenaline, which are produced from your adrenal glands, which are on top of your kidneys, and also from nerves which are part of your autonomic nervous system, the sympathetic nervous system. When adrenaline binds to these adrenoreceptors, they trigger the cells that carry those receptors to change their activity. And different tissues in your body have different adrenoceptors. And the heart has a class of adrenoceptors called beta-1 adrenoceptors. And when adrenaline and noradrenaline locks on to those beta-1 receptors, what they do is to make the heart beat more quickly. And the reason they make the heart beat more quickly is that they make heart cells allow sodium to get into the cell more quickly than it would do normally. And this makes the cell get more electrically excited than it would do normally. And as a result, the cell fires a pulse much more quickly than it would do normally, so the whole heart beats more quickly. If you give beta blockers, these are drugs which look a bit like adrenaline, so they bind onto the receptor, the docking station, the same way adrenaline would, but they can't activate it. It's a bit like shoving a key in a keyhole, but it's the wrong key for the keyhole. It'll go into the keyhole, but it won't turn the lock. But while the key is in there, you can't get the right key in to unlock the lock. So as a result, the heart can't see adrenaline which is washing around in the bloodstream or coming out of your nervous system. So as a result, the heart thinks, well, I'll just beat at my normal rate, which is much slower. And so it brings down heart rate. And because heart rate also determines your blood pressure, because it also determines how hard the heart beats, your blood pressure comes down too. So that's why you can take beta blockers to both reduce anxiety, reduce heart rate, but also reduce blood pressure.
Now, Derek has called in saying that he suffers from prostatitis. I hope I've got that right. Can you let me know a little bit about it? I heard that tomatoes are good for your prostate. Is that true? And also he had a PSA check, 0.8. How reliable is this reading?
Yes, well, one thing that all men have in common is that they all have one organ that women don't have, which is a prostate. And this is a gland which sits inside at the bottom of the bladder. So it surrounds the neck of your bladder. And so the urethra, which is the tube that comes out of the bladder and goes down the penis, has to pass through the prostate gland. And the prostate gland adds various chemicals to semen. And these include prostaglandins, which are used elsewhere in the body for other processes, but in the course of ejaculation, they're actually used in actually they trigger, I'm trying to think of the word, peristalsis in the vagina, so it actually helps to get sperm where it needs to go. And so it's actually a very important job. But the problem is the prostate gets bigger as us blokes get older. It's called benign prostatic hyperplasia. And for some reason, the cells in the prostate continue to grow and enlarge with age. And so as we get older, the whole gland is getting bigger. And because it's getting bigger and the urethra has to go through the middle of it, then as it gets larger, it can impinge or squeeze on the neck of the bladder, and this can obstruct or slowly narrow the path through which the urine can flow. And so this is what eventually can lead to urinary retention, and people struggle to go for a wee. The problem is that because of the prostate getting larger through life like that, there's also a chance that it can also undergo a more worrying change, which is that you can develop prostate cancer. And this is very common. In fact, by about the age of 80, pretty much everybody has at least one focus of cancerous cells in the prostate. That sounds alarming, but actually it need not be too alarming for the simple reason that for the vast majority of people, they will never know that's going to be a problem because it's very indolent and it may never turn into anything. Many people may die with a problem they didn't even know they had, and they die of something else completely. That doesn't mean, though, we should be complacent about it, and it's for that reason that people are saying we need to have some kind of screening test or some way of making sure that men aren't developing a prostate cancer that is going to impact on their health.
Absolutely, like ladies have
cervical screening, breast screening,
absolutely.
People are talking about ovarian screening, yet there's nothing on the NHS for men. And men actually don't live as long as women. So I think it's all a little bit unfair, really. We need to do more to try and sort men's health out, really.
Yeah.
And the test that Derek's referring to, the PSA, stands for prostate specific antigen. And this is one test you can do which can give some kind of pointer or direction towards whether or not there might be something wrong with the prostate. PSA, prostate-specific antigen, is a protein which is produced by cells in the prostate which spills over into the bloodstream. And a healthy prostate makes a little bit. An unhealthy prostate makes a lot. A prostate which is getting larger will make a bit more. The problem is that it's very difficult to discriminate an unhealthy prostate, which is made at a certain level of PSA in the bloodstream, from a prostate that's healthy but just makes a lot of the PSA anyway. And so there's this very big overlap. It's not a very good test because it's not easy to discriminate someone who's healthy and has a high level from someone who's unhealthy and has an elevated but not necessarily that high level. So what doctors are looking for is a better test, which we can look in the blood for markers that might indicate there's something wrong with the prostate, without actually this blurring between healthy and unhealthy, because then it would be much more informative as a test. But PSA does have its place, and in someone who has a prostate cancer, for example, they may have very high levels of prostate-specific antigen, and when they receive treatment for that, they can then be monitored to see if their level of PSA stays very, very low afterwards, because if it suddenly starts to climb again, this can be an early warning that there's something worrying that needs to be investigated. You can go back for investigation and have it treated. So it can be useful, but it certainly isn't something that you should put all your faith in as a single one-off test.
What about diet then? Because we're going back to the tomatoes there.
Yes, well, one thing that's materialised in the last 10 years or so is that tomatoes are very rich in a chemical called lycopene, Lycopene. This is very powerfully antioxidant in its effects, and it seems to also have a protective effect against prostate cancer. And in dietary studies where people have followed up individuals and then compared what they eat with their outcome for various diseases, including prostate cancer, they find that people who eat a lot of tomato products, and what they're really going on about here is the Mediterranean diet, where people tend to eat lots and lots of tomatoes, especially Italy, that kind of part of the Mediterranean. In those circumstances, the risk of prostate cancer seems to be lower at any given age than in people who don't eat that sort of diet. So this strongly argues that eating a healthy diet rich in antioxidants can help to reduce the risk of prostate cancer, but that pretty much goes for every cancer. If you eat a healthy diet, you can reduce your risk across the board of pretty much all kinds of cancer, in fact any kind of disease.
Right, well, we're fast running out of time, Dr. Chris, but Annie has said one here. She says, as he's a consultant virologist, can Dr. Chris say how long I would need to be, say, next to someone on a bus to catch the new flu? If randomly caught, why? Because I think it was the new flu, so need to get tested, not just a bad summer cold. That's from Annie on the text.
Well, I hate to say it, but there's a lot of it about.
Yes.
And in fact, Australia has got very big problems because it's now their winter time, and they've actually stopped bothering to try to control it. They're actually letting it go now and spread through the population. Whereas here in this country, we're still exercising a process of identify cases and then try and give prophylaxis to people who have been identified and people who are contacts in order to try and stop the spread. The fact is, though, there's probably enormous amounts of this now out in the community and spreading. And actually, there's what we call a clinical iceberg. There are the cases we do know about, but there's almost certainly quite a big volume of disease or illness out there that we don't know about. But flu is a very infectious disease, and the chances are, if you have a close contact with someone for a significant period of time, and what that means is having a close conversation or having close contact with someone who's got symptoms, in other words, they're infectious, for just a few minutes, that can be enough, because you only need to breathe in a handful of particles of the flu virus, each of which is absolutely microscopically tiny, 1/10,000th of a millimetre across, and you can catch it. So bad news, I'm afraid, Annie. It's easy to catch. The good news is, though, that we're very good at diagnosing it, and it seems to be a fairly mild illness. So even if you have caught it, the likelihood is that you'll come out of it okay.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.